Everything is good. Cool. Well, I'm doing pretty well. Slowly getting used to teaching everything online, but I don't know. I don't know how you feel about online lectures. Do you have any strong opinions for or against? How are you finding it so far? Or is that like the way you're also taking other courses, or are other courses asynchronously taught? Like how is it so far for you guys? Oh, okay. Mm-hmm. All right. What about the others? How do the other folks feel? Well, I'm glad to hear that, Jacob. That's that's good to hear. Online format is definitely a little strange. Yeah, I agree with you. It's a little strange. It's weird. Um, I just, I guess I got used to having everyone physically in class and talking to them, and also like when I ask a question in a regular class, when we used to have physical classes or in-person classes, then you can tell whether people understand what you're saying, maybe they have questions, maybe you can sort of judge from the vibe of the audience, like how things are going. Uh, but with everything online now, yeah, I agree. It's a little strange. Yes, I agree with you as well, Akalanka. Losing in-person classes is not the best. Most are synchronous. Some of them are trying to build up lecture content to make the course 50-50. Okay. Yeah, I thought about I agree with you, Robert. I also miss in-person classes. I don't know how I'm going to handle 150 students in 2 to 9 next semester. This is going to be a crazy class. But we'll see. We'll see how it goes. Yeah, overseas students is also another challenge that we have to deal with because I mean my class is 12:30 Edmonton time, which is probably 3 a.m. somewhere. So yeah, hopefully things will get resolved soon, and that we'll be able to work through things and get back to normal. Yeah, it's beyond midnight for Mohaimin here, so there you go. I'm sure many would find it inconvenient. And I also found that, I don't know if you know that or not, but the university made it available that we can tell the geographic location of the students, I think through bear tracks or something. And I actually realized that some of those geographic locations are not correct. But it's the information that the university has so far. But um, course, probably one that makes the best use of streaming tools. Well, I'm glad to hear that, Eldon. Okay, great. Great to know that the YouTube lectures are hopefully proving useful. I learned a class late. English course. Well, I'm really happy to hear that the setup that we have so far is working for the most part. I admit that there are a few glitches here and there, but hopefully we'll iron those out as we go. And I also like, I'm also happy to see that rewatching lectures is kind of like the most popular feature of this course. I started doing that actually in my 2 to 9 course in the last winter, even before COVID-19 and whatnot. And then sort of the transition when everything moved online was relatively easier for me. And I'm planning to do that for all my lectures from now on in all the courses I'm teaching. I think just having the recordings there, even for archival purposes, is just useful, and it enables like anyone to watch videos on their own pace, or even make use of the translation, the auto translation features from YouTube. And you can download things offline. You can sort of add closed captioning. You can speed things up. You can slow things down. You can sort of do whatever you want on your own pace. So I'm happy to see that this is working for many people here. Cool. I sort of have a feeling that the Twitch live stream might be a bit glitchy, or buffering a little bit. So I don't know. Let me know if you are having any problems with that. But hopefully it will resolve itself soon. So with that out of the way, let's pick up where we left off last lecture. So in the last lecture, we saw together a couple of things related to static analysis, and we got introduced to the very first framework, the monotone framework in program analysis, where you want to have, instead of having a specialized algorithm for every single type of analysis, which basically means that for any new analysis that you will come up with, you will have to have a new implementation of the algorithm that will solve this analysis. So the monotone framework works around that problem by having a generic framework where you have the same algorithm that will solve the analysis problem, such that you can configure the framework with analysis-specific parameters. And in the previous lecture, we saw the first parameter, which is the analysis direction, whether the analysis would go forward in the program or goes backwards in the program. And the thing that will determine the direction of the analysis would be where is the information that you want to compute? Where does it live? Are you asking a question about, or is the information is related to something that may have happened in the past? So something like, is this value or is this variable holding a constant value, or has this variable ever held a constant value? So you want to check out the past history of that variable to answer this question. So for analyses like that, the analysis direction would go from the past to the future, so it will go in a forward direction. On the other hand, if the analysis is reasoning about a behavior of the program that has not happened yet and will still happen in the future, then your analysis has to go from the future to the current point in time, which would mean that the analysis will have to go backwards in the program. A prime example of that is liveness analysis or live variables analysis. So at a given statement, you want to know, would this variable be used in the future or not? Or will this variable be used later? So you will never be able to understand or to answer this question if you go to a past point in the program, but rather you have to go to a future point in the program to be able to know whether that variable will be used later or not. And for these kinds of analyses, for these types of analyses, the analysis direction will be backwards. And we briefly talked about how that basically a forwards analysis and a backwards analysis are implemented using the same algorithm in the monotone framework. The key difference here is that in the forward analysis, the analysis will solve the data flow problem along the control flow edges in the control flow graph, or the CFG. In the backwards analysis, the CFG edges will be reversed so that every edge, the tails are going to be heads, the heads are going to be tails, and then all the other edges will be reversed in directions, and then you're going to start solving the analysis problem on that reversed control flow graph. This is roughly what we have discussed in the past lecture or so. In today's lecture, we're going to move on to another abstraction of the analysis that we're going to talk about, which is the analysis abstraction itself, the domain that the analysis will be defined over. And this abstraction will determine how we are going to configure other parameters for the monotone framework, or for any algorithm that will be implemented on the monotone framework. Before I move on to the analysis abstraction, does anyone have any questions so far about maybe what we have discussed in the last lecture or so? Okay, cool. So far, so good then. All right. Just a quick question before I move on. Is everyone seeing the stream properly on their end? I'm seeing it a little bit glitchy and buffery on my end here. Just want to make sure that you're getting a smooth feed on your end. It's unwatchable from my end. It's lagging. Looks like most of your frames are dropped. Okay. The audio comes through. Mostly frozen for me. Okay. Well, if that's the case, let me actually just Still Zoom is not happy with my setup here. Okay, so just maybe give me a second. I will stop the stream and restart it again so that you're able to see the video feed of the lecture. So just give me a second here. I'm gonna restart the stream again. Hopefully this time it won't be lagging as before. All right. I hope that this is a bit better than before. So if you could just give me, all right, looks good so far, so good, great. So hopefully things will stay smooth as we go. So let's get back to it then. So as I was saying, in today's lecture, we're going to start talking about the analysis abstraction and how we're going to use lattice theory, and we'll get to that in a moment, to be able to define what the domain of the analysis is. What is the analysis going to be defined on? What are the type of values that the analysis is going to deal with, and so on and so forth. First thing that we should know is that the lattice that you should define as an analysis engineer will greatly depend on the analysis problem that you're solving. So we have seen, for example, constant propagation needs a different lattice than a nullness analysis, than a liveness analysis, for example, than a pointer analysis for that matter. So this is again one of those configurations that you can change within the analysis itself to still fit within the monotone framework. So for example, here we have a constant propagation analysis, and we basically have a straight line of code here in a Java-like language. So here we have A equals 1, then B equals 2, then you assign null to O, to the object O, and then you assign a new object to O, and then you call a variable on that object O. So if we're doing a constant propagation analysis, what is really the question that we want to answer here? The question that the analysis is trying to answer is, what is the constant value of x at a location S, or at a statement S, right? And for that, you may start with an empty set, and then you may assign the value 1 to A after this statement. And then right before O equals null, the values that you're going to have are going to be A will be assigned the value 1, B will be assigned the value 2, right? So this is going to be for a constant propagation analysis. If you have a nullness analysis, then the values that your analysis is computing are going to be substantially different. Why? Because the answer now, or the question that we want to answer now, is which variable is going to be null at a location S. So I don't care about the constant integer or float value that, or floating point value that the variable may hold, but I want to know if that variable is going to be null or not. So I want to keep track of objects that may point to null, and any other variable, any variable that may point to null, and any other reference or variable would just be pointing to a concrete object. So in this case, empty set before we start, empty set after the first assignment statement, because A is pointing to 1, so it's basically a don't care kind of fact for the analysis. Same thing after B equals 2. Now for this statement here, O equals null, I know now that O points to a null reference, or has been assigned a null reference, so I'm going to add it to my set of facts that I'm computing along the way. And then when that O is being assigned a new object O, so now I'm assigning it a concrete object, I'm going to remove it from that set, yielding that empty set. So this lattice that I'm going to use in this kind of analysis is going to be quite different than the one I'm going to use for constant propagation. Type analysis is a third kind of analysis that would require a completely different also kind of lattice. Here I'm basically I have a mapping basically more or less between an object type and the type that it points to, so that I can just look up that object and then figure out whether what is the runtime type that this object may point to when or if that program runs in real life. So as you have seen in all those examples, if you notice, lattices that I'm using for any of those analyses, yes, they are different, the contents are different, the items in there are different, but the lattices are more or less sets of something, right? They are often like a set of something, some items that go into that set, right? So why don't we just use sets instead of having to define yet another mathematical or theoretical abstraction? So why do we need to define this lattice in the first place? Why can't we just use sets in the regular sense? So let's have an example here. So let's assume that we are defining the lattice as just being sets, right? And in this example here, I'm just showing you the control flow graph of a piece of code in a Java-like language, where here we're assigning x to the value, we're assigning 0 to the value x. Then we have a conditional, and based on that condition, either if it's true, if the condition is true, then we're going to increment x plus plus and then go back to that condition. So this is some sort of a loop construct, whether it's a while loop or a for loop of some sort. And then if it's false, then I'm going to exit the loop and I'm going to end my method right now. All right, so if I'm using sets instead of lattices, what I'm going to do here is that x, I'm going to assign x the value 0, right? I'm going to assign x the value 0 here after the first statement, and assuming that I'm going to take the body of the loop, before executing the body of the loop, x again will be assigned the value 0. So this is going to be my result. And after executing x plus plus, the value of x will become 1. And then let's assume I execute the loop again. Then the value of x will become 0 or 1, because 0 I got from the first iteration of the loop, 1 I got from the second iteration of the loop. And then x after that statement will be 1 and 2. Again, 1 is from the first iteration of the loop, 2 is from the second iteration of the loop. Then I'm going to execute it again, so I'm going to have 0, 1, 2. Then x after the statement will be 1, 2, 3, and so on, and so on, and so on. And this can go on forever, as long as, or for however many iterations that this loop may go on for, which I don't know at compile time. Remember, like, we're doing all these kind of analyses at compile time statically without knowing what is the actual runtime behavior of the program. We are trying to over approximate it. So if I don't know how many iterations the loop may go for, I'm going to have to assume that it may go on for as long as possible. So this is why we don't use sets, because if we are going to use sets in this abstraction here, we need to have a set that has an infinite number of elements in it, and we can't have that defined as such. So instead of having sets, we're going to gradually build up our lattice using some set theory and some mathematics here. So the first thing that we're going to use to be able to build our lattice is going to be partially ordered sets, or posets. So what do they mean? They basically mean the following. So a partially ordered set is a regular set in its mathematical sense. So you have a set from that universe, and you have a binary relation that is defined on that set. This is not a subset relation or subset equal. It's a binary relation that is defined on that universe U, such that U as a set and the binary relation will form a poset if the following conditions are all satisfied. The first condition is the following. If you have the poset, if you have that relation reflexive, meaning that every element in that set U is related to itself through that binary relation, then that binary relation is reflexive. So this is the first condition. For all elements X in U, X is going to be related to itself through that binary relation. So reflexiveness is the first condition of that binary relation. That's the first point. The second is transitivity. So what do I mean by that? So if you read the mathematical abstraction of this, or the mathematical formulation of this statement, it will say for all X, Y, and Z, they are all elements of U, and if X is related to Y and Y is related to Z, then X is related to Z. Or you can say X is partially ordered by Z. That would mean that this binary relationship is transitive, because the transitivity property comes from the fact that Y basically dominates X in this relationship and Z dominates Y in this relationship. So I can say that Z dominates X in this relationship. So for example, here we have D3 is related to D2 by this relationship. So in this case, D3 would be the X and D2 would be the Y. We also have D5 is going to be, just give me a second. So in this case we have D5 is X, D3 is Y. So Y is related to X through that relationship. D2 is Z. So D2 is related to Y, which is D3 through that relationship. And from that I can deduce that X or D5 is related to D2 through that relationship. So this is transitivity. So the first is reflexiveness, second is transitivity. The third property or the third condition that has to be satisfied for this binary relationship to, along with the set to be a partially ordered set, is that it has to be anti-symmetric. So what do I mean by anti-symmetry? I mean the following. I mean that if X, Y, and Z are all elements of that set, X is related to Y with that relationship, and Y is also related to X in that relationship, that can only mean one thing. It can only mean that X and Y are the same element. This is what anti-symmetry is. You cannot have two elements where the relationship is bidirectional, going in both directions, unless both elements are the same. So you cannot have something that says D3 is related to D4 and D4 is related to D3. This is going to be wrong here. This cannot happen in a partially ordered set. So for example, D3 cannot be related back to D5, otherwise this is not going to be a partially ordered set. So the first construct, a pole set or a partially ordered set, you have a set U in the regular sense in mathematics, and you have a binary relationship. A binary relationship means it's a relationship that is defined over every two elements in the set. This relationship has to be reflexive. Each element is related to itself. This relationship has to be transitive. You can have an intermediary item that relates two elements to each other. This relationship has to be anti-symmetric, which means that if you have X is related to Y and Y is related to X, they have to be the same element. You cannot have them as different elements. So if those three conditions are satisfied, then this is going to be a pole set. So we have a question here that says, does anti-symmetric guarantees monotone property? It is one step further to guarantee monotone property, but we're going to get to that in a few minutes, CG. So hold on for a few minutes there, and we're going to get to that. But it will help us to establish this guarantee. But not on its own. It has to be combined with a few other things. Does anyone have any questions so far? Pole sets are really a cornerstone of what we're going to discuss in today's lecture and also on Tuesday. So if you've got any questions about it, I'm happy to answer them right now before we move on to any other topic. So far, so good. All right. Um, cool. I'm just gonna try something really quick. Um, just trying to fix the problem with Zoom here. Okay, I saw a setting where I can actually have my iPad screen be the background of my Zoom call, but it seems that I can't find it now. I'll try to fix that for future lectures because I noticed that the stream is lagging a little bit and it might be frustrating to some of you here. So I will try to fix it for our next lecture. All right. So now that we have established what a partially ordered set is, let's see how we can use that to build up our lattice. One thing before we move on, really what we mean by what does it mean that X is related to Y in this poset relationship, in this binary relationship. It basically means that Y in this case is going to be a safe over approximation of X, or is going to be at least as sound as X. So in other words, let's say that D1 is our X, D2 is our Y. It basically means that if the analysis should have computed D1, but instead computed Y as a result of the analysis, this is going to be okay in the sense of the over approximation. That means that you're going to still capture the capture the runtime behavior of the program, but not as precise as your analysis should have done. You're just over approximating that result, which is fine because you're not going to ignore or miss any behavior that your program may happen at runtime. This is really the essence of what the meaning of that binary relationship is. It's just a way of ordering the items or the values that your analysis is computing over such that the analysis results will be a safe over approximation of the actual runtime behavior of the program. All right, so now that we have a poset, let's have a few examples of what posets are. So the first example is the less than or equal relationship with natural numbers, right? So how do we check that this is going to be a poset? Well, we have three conditions that we have to satisfy, right? The first condition would be reflexive. And basically that means that X will have to be related to itself. So when you're talking about natural numbers, that set of natural numbers is basically 0, 1, 2, 3, all the way up to the end of numbers. So if you pick any element of that set, would it be related to itself? Would it say, for example, let's pick an element, 1, and this relationship is going to be less than or equal, right? So, oops. So 1, is it less than or equal 1? Is that true? Yes, it's true. 1 is less than or equal 1. Is 2 less than or equal 2? Yes, that's also true. They are less than, 2 is less than or equal 2. Then the second check that we want to have is transitivity. Transitivity. I cannot write down things. So transitivity means that if X is less than or equal Y, and Y is less than or equal Z, then X is going to be less than or equal Z. So let's pick a few numbers here. So let's say X is going to be 2, Y is going to be 5, and Z is going to be 7. So 2 is indeed less than or equal 5, and 5 is indeed less than or equal 7. Does that mean that 2 is less than or equal 7? Yes, that's correct. And it's true for all three pairs, for all tuples x, y, and z that are defined here. Third, anti-symmetry. which means if x is less than or equal y, and y is less than or equal x, then that should only mean that x is equal to y. So let's find that out. So 2, let's pick x to be 2, and y would be 3. So is 2 less than or equal 3? Yes. Is 3 less than or equal 2? No, that's not correct. So I cannot pick y to be 3. So what can I pick y? What would be the value of y that will satisfy that second part of the condition here? So 2 is less than or equal 3 and 4 and 5 and 6, but for y to be also less than or equal 2, I can only have 2. So both x and y have to be 2. So that proves that if x is less than or equal y, and y is less than or equal x, then x has to be equal to y. So this is the first example of a poset. If you want to try out something on your own, maybe at home, and come back to me next lecture to figure out, to maybe discuss it, try out the same exercise with x, with natural numbers as your set, but your binary relationship is less than, not less than or equal. And try out the same kind of quick testing and check that we have done here to know whether this is going to form a poset or not. Similar to that, we have the subset relationship, not the strict subset, but the subset relationship over finite sets. This is also going to form a poset, a partially ordered set, because it satisfies all three conditions for you. So overall, the key takeaway about partially ordered sets or posets is that it is basically a set with some notion of ordering of less than or equal, more or less. This is really what, if you wanna boil it down to something that you can remember it with, it's basically a set where you can define a less than or equal ordering over all the elements of that set, or all the items in that set. If you can do that, then you have got yourself a poset, and you can move forward with other definitions as well in lattice theory. Before we move on to the next part, I want to discuss some notion called hash diagrams that we have been actually using in the previous couple of slides, but I haven't really formally defined them. And it's going to be important because you're going to see it quite a lot, both in the lectures, in today's lecture and on Thursday, and also in the research papers that we're going to read, and most definitely you're going to see them when you're drawing things or you're solving the assignments as well. So what is a hash diagram? It's basically a diagram where you are drawing a lattice. So it's a graphical representation of what a lattice is. So this is an example of a hash diagram where you have finite posets represented as a diagram or as a graphical structure of some sort. Every vertex here, all the vertices here, would represent elements of the set U. So items or elements of the set U. Any line that you're drawing from an element to the other would represent a relationship defined by that binary relationship. So if you draw a line from D2 to D1, that basically means that D2 is defined with that binary relationship to be less than or equal D1. Defined to be less than or equal D1. So this is what we're going to use in our notation from now on to draw lattices and posets. We are going to assume reflexivity here. So I'm not going to draw like self loops. So I'm not going to draw self loops like that. This is going to be assumed. And the other thing, I am also not going to draw transitivity. So I'm not going to draw the fact that if D3 is related to D2 and D2 is related to D1, I'm not going to draw this edge here. So all these are going to be assumed. So I'm only going to draw the explicit edges that are defined by the binary relationship, and just assume that since it is a poset, transitivity holds and anti-symmetry holds and reflexivity holds as well. And we're not going to draw them just so that we don't clutter the diagrams that we're going to use for drawing the pole sets. Does anyone have any questions so far? I'm gonna stop here for a short break for a few moments before we move on to defining other aspects of pole sets or lattices or lattice theory. So maybe now it's it's 1:10 almost. So maybe let's reconvene at 1:15. So have a short break, drink some water, stretch your legs. Feel free to ask me any questions on the Zoom link, on the Zoom meeting, sorry. And I'll be happy to answer them. Having a silent break like that reminds me of my offer to you folks here. Would you rather we play some music during those breaks? And if you do you have any suggestions for that? Maybe not. Anything is fine by me, alright? All right. Welcome back, everyone. Let's continue our lecture for today. So before the break, we talked about posets and partially ordered sets and how they're going to be the main cornerstone or the building block for building our lattice. To be able to define the abstract domain that our static analysis is going to be operate on or compute values over. So what else is needed to be able to create a lattice given our poset already, which is a set with a binary relationship that is reflexive, antisymmetric, and transitive. So a few things that are still needed. The first is we need to have something called an upper bound. So an upper bound is basically the following. So if you already have a poset defined defined as the universe U or the set U and the binary relationship as such, and you have A, which is a subset of U, so it doesn't have to be one element, it's a subset of U, and Z, which is an element of U, then we're going to say that Z is an upper bound of A if and only if for all elements in that subset of U, Z is dominating or is greater than, quote unquote, given that binary relationship, every other element in A. So again, so you have a set U, you have a subset of that set called A, and you're going to say that an element Z is going to be an upper bound of that subset of U if it is going to be of a greater order or a larger order or a higher order than every other element in that subset in A. If that's the case, then I'm going to say that Z is an upper bound of A. So for example, you have this poset here, so D1, D2, D3, D4, D5, and assuming that A, for example, is going to be D1 and D3, and I'm going to say that Z is going to be an approximation, right? So remember, like the essence of this binary relationship here is that Z is a safe approximation or over approximation of the elements X. So here I'm going to say, So here I'm going to say that Z is going to be an approximation of every element in A. I can basically substitute all the elements in A with that one element Z. Wait a second. I think I might have missed a slide there. All right. So this is if we have a subset in U. In other words, alternatively, what if we don't have a subset of U? What if we have just an element or two elements or a few elements in our universe U? So again, we have our poset, and we have we have three elements of that poset, X, Y, and Z. And we're going to say that Z is going to be an upper bound of the elements X and Y. So you have elements now, not sets. We're going to have elements of that set. And we're going to say that if Z has a higher order than X and Z has a higher order than Y, then Z is going to be an upper bound of both X and Y. So you can also think of this in terms of, you still have this previous definition on the previous slide, such that A is going to be equal to X and Y. And indeed, that's what this blue box down there says. So again, you have the same definition, but now you're specializing A to be X and Y. So if you have that, again on the same Hass diagram, if this is D1 is going to be X in this case, D2 is going to be Z. So Z does indeed have a higher order than X, given that poset. Again, D3 is going to be Y, D2 is Z. So again, Z has a higher order than Y. So that means that D2 is going to be an over approximation or a safe over approximation of every element in A. So basically what I can say is, if I'm after computing an analysis result that would involve either elements of A or any element in A, D2 would be a safe over approximation of that. I will be satisfied if I get that result. Yes, it's not going to be the precise result, but it is a safe approximation or a sound approximation of the actual result that I'm looking for from that analysis. So now that we have defined an upper bound, what we actually truly want is something called the least upper bound, the most tight or the most precise upper bound that we can get. That's basically what it is. So given a pose set, U with a binary relationship, and again, you have a subset of that pose set, I'm going to call the least upper bound, or I'm going to call an element Z to be the least upper bound of A if the following is true. So assuming here that we have A, so the D3 and D5 would represent my subset A. If, number one, X is an element of A, for every element of A, Z must have a larger or a higher order than this X. So the first thing is Z must be an upper bound. The first of all, for it to be a least upper bound, first of all, it has to be an upper bound in the first place. Then let's define what that least part here means. So it is an upper bound, and that's the first thing. But the second thing also, it is not enough for it to be an upper bound, but it also has to be the closest upper bound to those elements in A, or the least upper bound to those elements in A. So in other words, there might be other upper bounds that could be defined as well. So in this case here, if you're talking about A, D2 is an upper bound, right? Why is D2 an upper bound? Well, let's find out. So what does it take for D2 to be an upper bound of A? It has to be an upper bound of every element of A. So it has to be true that D2 is an upper bound of D3. Is that true? Yes, it's true, because according to that relationship in that diagram, D2 is indeed an upper bound of D3. The second is D2 an upper bound of D5. So we know that this is true. Is that second property true? What do you folks think? Does D2 dominate D5 or has a higher order than D5? And why, of course? So I'm seeing, all right, so yes, and because of transitivity. Can you elaborate a little bit more, Akalanka, about the transitivity? So how did you deduce that transitivity relationship here? Mm-hmm. Right. So D2 is going to be a higher order than D5. Yes, exactly. So D2 directly has a higher order than D3 through transitivity, because that relationship is transitive. So D2 is going to have a higher order than D5. So that's why. So now we have those two are going to be true. So D2 could be an upper bound. Similarly, D4 is also going to be an upper bound of those. So we have three upper bounds in this pose set here, not just one, but three. Well, which one of them is going to be the least upper bound? So we need to have a second condition to be able to determine that. So the second condition for the least upper bound is that if you have y, or for all y's that are elements of U, for each one of them, Z must be dominated by that y element. So what that basically means is, if you have other upper bounds, those upper bounds have to have a higher order in the poset than your least upper bound. So basically, this element here talks about being the upper bound, and this condition here talks about being the least upper bound. Least here means has a lower order in the poset compared to the other potential upper bounds, right? So if we apply that to here, we have three upper bounds that we determined, right? So D4 is an upper bound, D2 is an upper bound, D3 is an upper bound. However, if we look at the diagram, if we look at the poset, we will find that D3 has a lower rank than D4, right? D3 also has a lower rank than D2. So that basically means that D3 is the least upper bound from all the upper bounds that we have found so far. So if I'm looking at A, D3 would be the least upper bound here. Or in other words, least as well here could mean the most precise approximation of the result that belongs to A. So this is another way to formally write this. So to formally write the fact that Z is the least upper bound of A, using this, not the union relationship again. It's going to be the square upper cup, or the square cup, basically. That basically means that Z is the least upper bound of A, of the subset A, of the relationship. You might also see that in some of the papers that we're going to read later in the semester. So far, so good. Any questions about the least upper bound in posets? Going through the notation of the second condition. Yes, of course. So what does the notation of the second condition say? So the notation here says the following. For all y, oops. So the notation here says the following. It says for all y that are elements of U, so for every element in the set, if you have y that has a higher order than every other element in that set A, so basically this part here means that y is an upper bound of A. So if you look at all the elements in the universe, and you found that, so for every element in the universe, and you find that this element dominates or has a higher order than all the elements of that subset A of the universe, so meaning that y is an upper bound of that subset A, Z must have a lower rank or a lower order in the relationship to that element y. And if that's the case, then Z is going to be the least upper bound of them all. So basically this part here is about figuring out all the upper bounds in the relationship. And here, that part here specifies how this upper bound or which upper bound will be the least one, that it has to be dominated by all the upper bounds or the other upper bounds. Does that answer your question, Ridwan? Okay. So there can be no least upper bound for some subsets. Well, I am interested here just for the least upper bound for the subset A. I haven't talked about having a least upper bound for all subsets yet. We are going to see that in a couple of minutes. So you're just a couple of minutes ahead of me, Mohammed. All right, cool. Thanks, Ridwan. Any other questions so far? Okay. I don't think there are any other questions about this part, but if you have any questions, just drop me a line on the Zoom chat and I'll stop explaining and I'll get to your question right away. All right. So now that we have defined what a least upper bound is, can you have more than one least upper bound in your poset for a given subset A? So let's go back here to this definition. My question now is, can we have more than one least upper bound in this poset, in this scenario here? And if it's true, why? And if it's false, why not? It might be easier if you, rather than writing things down, or to just like voice out your thoughts on the Zoom meeting, rather than just writing down like mathematical formulas on the chat. So if you find that to be easier. So the question again is, having said that, can I have more than one least upper bound? Is it the reflexive property or something else? You're close. It has to do with the properties that we defined on this binary relationship, right? So what is the property that you think will be not true? Antisymmetric, right? So what does it mean that we have more than one reflexive, more than one least upper bound? It would basically mean that Z would be a least upper bound. So that means that Y will be, we're going to have Z, we're going to have some value, some upper bound Y that is a least upper bound, but we might also have the other way around. So Z might also be a least upper bound. But for this scenario to be true, oh, sorry, that's not what I meant. For some reason, I can't seem to erase things on my keynote presentation. So I have to do it the old-fashioned way with undoing all my edits. So going back to here, and the question, can we have more than one least upper bound? If we can, assuming that we can have more than least upper bound, what does that mean? That means that we can have a Z that is dominated by Y, right? For all Y's here in that regard. But I can also have the scenario as such. And there's only one way that you can have this, that you can have these two conditions if you have a least upper bound. And for you to have this, Y has to be equal to Z. But Y is not equal to Z here because Y is just not the same value as Z according to this condition here, which will defy, again, which will invalidate the premise that you have two different least upper bounds. So if you assume that you have two least upper bounds, you're going to come up to a conclusion that will contradict that assumption. So you cannot have two least upper bounds because of the anti-symmetric property of the binary relationship that guards or that orders basically the elements or the items in the set or the poset. So because of anti-symmetry, you cannot have more than one least upper bound. Does that make any sense, everyone? Okay. Any questions so far? All right. So now, equivalently, like we have talked about having a least upper bound, and that will guard the upper bound of the poset. We can talk about having a greatest lower bound in sort of the reverse fashion. So everything that we have defined as an upper bound, we can also define an equivalent or a counterpart that's a lower bound to the poset by just reversing the ordering of the relationship. So here we have basically the only difference here is that we want to find a lower or an element that is the lowest order of that subset A that we have. So in this case, if A is the elements D3 and D5, so it's a subset of the universe that we have U, we're going to say that Z is going to be the greatest lower bound by having this reverse square cup notation in mathematical notation to signify that if Z is a lower bound, so Z has a lower bound than all the elements in that subset, and if there exists, again, following the same notation, that this means that Y is a lower bound. But since I'm talking about the greatest lower bound, Z has to have a higher order than all the other lower bounds for it to be a greatest lower bound. So now we have defined a least upper bound and a greatest lower bound for a subset A in the poset. So now we can start defining actually our lattice. So we have defined a poset, we have defined the least upper bound for subsets of the poset. For a subset in the poset, we have defined a greatest lower bound in a subset of the poset. So what does it mean then to have a lattice? It means the following. So again, you have a poset where it is non-empty, so you do have elements in the universe U, then that poset is going to be a lattice if and only if for all elements X and Y that are in U, you have the following. So again, assuming that this is going to be the poset, you're going to have for any two elements in that poset, you're going to have a least upper bound. So you're able to define a least upper bound for those two elements, and which is going to be called the join of those two elements. And you're able to define a greatest lower bound for those two elements, which is going to be called a meet. So now these are two terms that we're going to use quite a lot extensively in the assignments, in the papers, in the readings that we have assigned in the course in the future lectures, and also in the lectures themselves, of course. So you have a poset. You can define your subset A to be any two elements in the poset. You should be able to determine a least upper bound, which is going to be called the join. You should be able to determine or compute the greatest lower bound, which is going to be called the meet. If you can define the join and the meet of any two elements in the poset, then you can call your poset a lattice. So this goes back to a question that was asked a few minutes ago, and I forgot to, I think it was by Mohaimin, I believe. exactly 10 minutes ago now. That what if we don't have a least upper bound for some subsets? If that's the case, then this is not going to be a lattice. It is missing some definitions of a least upper bound for some subsets in the lattice. Okay, so great. So now we have our own lattice, right? What if we don't have some of those upper bounds or least upper bounds or greatest lower bounds? So we can still call them, we cannot call them a lattice, but we can call them a semi-lattice. And we can call them a joint semi-lattice if what is missing is we can still define a least upper bound for all of them. So these are called the join, but we cannot determine the meet of some of those of some of those subsets. So if you're able to determine only or compute only the joins of any two elements in the lattice, then this is called the join semi-lattice. Alternatively, if you're able to determine only the greatest lower bound of any two elements in the lattice, that is going to be called a meet semi-lattice. If you're able to determine both, then it's both a join semi-lattice and a meet semi-lattice, then this is going to be a full lattice that we're going to use from now on to determine or to abstract the domain of our analysis. So, any questions so far before we go on through a few examples of a few Hasse diagrams and determining whether they are lattices or not? This is going to be an exercise that we're going to end the lecture with probably today. Any questions? About posets, least upper bounds, greatest lower bounds, upper bounds or lower bounds, semi-lattices, join semi-lattices, meet semi-lattices or lattices in general. All right. I don't see any questions coming in through the Zoom chat, so I would assume that we're all good to go then through that exercise. Okay, so I'm going to ask you a few questions. I just want a yes or no feedback on the Zoom chat regarding those questions. So the first question is this Hasse diagram, does this stand for a lattice? So this is the only thing that you have in the Hasse diagram. Does this represent a lattice? Okay, so we have one yes. Any more yeses or nos? Okay, 2 yeses. 3 yeses. Anyone saying no? This would have been a lot easier in an in-person class. I can just tell what people are thinking about. All right, so indeed, this is going to be a lattice. It's a valid lattice because why is it a valid lattice? Because I'm able to determine a least upper bound for any two elements x and y in the universe that I have, in the set that I have, which is only a set of one element a, and I can also define a greatest lower bound. So a is going to be the least upper bound of itself, a is going to be the greatest lower bound of itself, and there's only one element a, so we're good to go. So this is going to be a valid lattice. What about now? Is this a lattice? Where A, B are elements of the lattice and B is has a higher order in the lattice than A. You can also just respond with a yes or no on the Zoom chat. Okay, a couple of yeses there, 3 yeses, 4 yeses. Would anyone, oh, 5 yeses, okay. Would anyone from those who said yes would like to say why? B is join, okay. A is meet. Great, right? So we only have 2 elements, so we don't have any option really of determining what the subsets A are. They only have one subset, AB. I mean, you can have more subsets if you want, like a set of A or a set of B, but B is going to be the join, A is going to be the meet. That's correct. So this is going to be a lattice. What about now? Is this a lattice? So you have A, B, C ordered according to this binary relationship here. Still seems to be yes, right? Okay, so I'm seeing now a few more yeses there. Yes. Stream is a bit behind. Okay. I think it's about 10 seconds behind or so. I'll try to take that into consideration when I'm posing my questions. Yeah, I don't know why Twitch is not doing very well today. I'll see if I can work something out for our next lecture, maybe. But yes, this is going to be a lattice again. So C is going to be basically the least upper bound, and A is going to be the greatest lower bound. What about now? This is a little bit more interesting. Is this a lattice here? So you have this kind of diamond-shaped Hess diagram. Still yes. Okay. So what would be again the join of this lattice here? Would it still be C or would it be something else? C is join and A is meet. All right. Again, you're all correct, those who responded. Yes, this is going to be a lattice because pick any 2 elements of this lattice here, or this poset rather, and you'll be able to determine a least upper bound and a greatest lower bound. They are defined for any 2 elements of this lattice here. So what about now? So now I'm just giving labels to those values here. Is this going to be a lattice? It's exactly the same poset as before. I just changed the symbols. So yes, it is going to be a lattice. And in fact, this lattice here is a special lattice that has a special name called the sign lattice. And if you check out one of the textbooks that I linked to in the resources for the class, which is the static analysis book by Anders Muller and others, you will see, and it's also a classical example of lattices given in many static analysis books. You will see that this sign lattice represents a lattice that will determine the sign of constants that may be used, for example, in constant propagation analysis. So here you can determine whether a value is going to be positive or negative or going to be 0, right? It's a positive value, a negative value is going to be a 0. So you can determine the sign of variables and expressions in your program. And these are going to be special values that we're going to talk about probably in our next lecture, not today. This is basically called top, and this is called bottom. So this is indeed a sign lattice. What about now? Is this a lattice? So I only added 2 elements, F and G. Does this represent a lattice? Does this Hasse diagram represent a lattice? So I have a comment here that you cannot find the join, right? So where exactly do you mean that, Mohammed? Where can you not find the join? There is nothing upper than both F and G. Right. So if I look at the elements F and G, for example, or even F and C, or C and G, I won't be able to find a least upper bound for any of these. So not only do I have one subset A, or one pair of elements that doesn't have a least upper bound, but there is 3 of them. So indeed, this is not going to be a lattice because I don't have a least upper bound. I do have a greatest lower bound though, so I can always find a meet for that. So this is going to be a meet semi-lattice. So this is going to be, this is going to be a meet semi-lattice, but it is not going to be a full lattice. I spoiled that one already. So I was going to ask, is this going to be a lattice here? And the answer, I already spoiled that. It's going to be no, it is not going to be a lattice. And the reason here is the following. Again, you cannot find for C and D, you won't be able to find a least upper bound for either of them, but you can find a greatest lower bound for them. So you won't be able to define a least upper bound for those. So again, this is not going to be a lattice. This is going to be my last example for today, and I see that I'm already over time limit, so I'm gonna stop here. I'm gonna continue from that example in our next lecture on Tuesday, and after that we are going to go through just a couple more examples, and then we're gonna discuss briefly again and summarize what we have discussed about lattices, and then define a couple more notations regarding lattices and having a complete lattice and so on. And once we have that, we're going to determine a few more properties about lattices. So lattices are going to stay with us for a bit in the lecture next Tuesday, on Tuesday next week. Once we have that, we're going to be able to determine now how we can define the domain of our analysis, which is the biggest thing that a static analysis engineer would have to determine and define properly, because that is going to affect all the other parameters that are going to go into the monotone framework, like the initial value that you have to determine, and the flow functions, how the flow functions are going to operate, and so on and so forth. Once we have that, I expect that this would take most of the time on Tuesday. We might have some examples there as well. Once we define that, we're going to go on to define flow functions and conclude that probably on Thursday next week, but we'll see. But most probably we're going to be done with this whole topic, which is one of the major topics that we're going to go through in this course on Thursday next week or so. Thank you everyone for joining me today. It was a pleasure talking to you all. If you have any questions regarding the assignment, don't forget it's going to be due tomorrow. If you have any questions, please continue to post them on eClass. Ifaz and myself will get to you as soon as we can. Don't forget also that the due date of the assignments is not midnight, it is 5 p.m. Edmonton time, just so that we make sure that Ifaz and I are available to you until the last minute of the working day in Edmonton. So please account for that when you submit your assignments on eClass. That will be all for today. Thanks again. Hope you have a nice weekend and see you on Tuesday next week. Thank you, everyone.